If you ever wondered how to access LIDAR-derived digital terrain model data, this is the place to be. In today's tutorial, I will show you not one, but 7 such data sources and how you can easily download this data, load it into R, and then the second part, how you can create very crisp 3D topographic maps with the help of Rayshadr, and also adding OpenStreetMap features to enrich your map further. All right, so our first LIDAR data source is Swiss Alti 3D, which is a service providing very high precise digital elevation models. So if you scroll down, you will find this download service over here where you can select how you want to export. So there are actually 6 ways here, or 5 ways. We're going to go for rectangle. We're going to click then on this new rectangle, and then we're going to zoom in, and you will see now these grids. Each of these grids is actually one of the these LIDAR files at a resolution of 0.5 meters. So what we're going to do next here is we're going to click here for the area we wish, and then we're just going to drag, and then we're going to release. And then we're going to scroll actually down, and over here what you will see is, first thing is the format. So how you want to export this, we're going to go for GeoTIFF. Next one is a resolution. So it has 0.5 meter resolution, so it's pretty crisp. That's one option. The other option, which I didn't show actually here, is that you can also select, for example, 1. And then the final one is the coordinates reference system. We're just going to go for the local Swiss coordinates reference system. And then we're going to click here on search. So when we click on this, it is actually going to give us those 4 tiles from this grid. And what you can do is either you can go ahead and individually download each of them, but what we're going to do instead is we're going to click actually on this link above, which is called Export All Links. And what this is going to do then is this is going to then download to our local drive an Excel file with all those 4 links that we need. So what we're going to do next is then we're going to fetch the name of this file, and then we're going to go into R and then issue directly from R a call to download these 4 GeoTIFFs to our main working directory. So once you download this file, you should head to the folder where you downloaded, and you should search for the CSV file here. So what we're going to do next is simply you're going to select then this one, and then you're going to go and copy the name of this CSV file. Then before we do anything else, we're going to first of all go and install the Pacman package, which is going to help us easily install and load the libraries that we need. So we're going to call pload function for Pacman for that purpose. And then we're going to actually go ahead and install and load the packages we need. The first one is Terra for working with raster files. We're going to be working, of course, with the digital elevation model. So we need this one. Tidyverse. For cleaning up, you will see the Swiss file, the CSV file. We will need this one. Asset package, definitely we will need for working with the polygons. Terrain R for issuing call to USGS webpage, so we can get LIDAR data for some small extent of US. OSM data will be definitely working heavily today with OpenStreetMap data. So we need this package to fetch roads, rivers, and buildings, and for example, names of places. MarMap we're going to be using for creating our customized color palette for the digital elevation model. And finally, Rayshadr will be using for creating a 3D map. Okay, so our next step will be to actually load this CSV file into R, and we can use readr from Tidyverse to do that. We just need to paste that name that we previously copied, add CSV, and also make sure that this is in the string format. Then we're going to print this table to see what's going on, and you will see now that we actually have 3 rows and a column name with the link. So this column name is also a valid link, which means that we actually need to combine both the column name and these 3 rows with the link. So in our case, in other words, the column name is the valid link. So in the next step, what we're going to do is we're going to be indeed combining those 3, and then we're going to be creating a single vector file. So to do that, we will be creating actually a new object, which I call here links vec. And then we're going to take the names of the links data, which is basically that column name. And then we're going to be taking also the first column or the values from the first column, which are going to be those 3. Now, if we print again, this is what we will see. Now we have actually those 4 links in one place. This is great. Now, having this in one place, the next thing will be to download each file to our local drive within using, of course, a loop. So first of all, I'm going to here define the names of these files. So using this Swiss LT3D. Then I'm going to use lapply, and I'm going to do a sequence along each of the members of this vector. And then I'm going to write a function after that, which is going to actually then issue the download file for each of these. So creating a loop using the lapply function in base R. So I'm going to apply this to this links vec for a destination file name. I'm just going to create here a name based on, of course, this name, each of these files, and then every one of them needs to have this diff extension at the end. Now, once I'm actually done with that, I can go ahead and run this, and this is, as you will see now, start downloading all these files, and it's actually going to finalize by downloading actually also this 4 file. Alright, so once we download these local files, we want to actually fetch them directly into R. So what we will do first, we will get first the names of the raster files that we're downloading to our local drive. And for that, we can use a list files from base R to do that. We'll first define actually, however, our main working directory. So I'm going to call it main dir. And then within this raster files, I'm going to set this as our main path from which I want to check that and fetch those. Then for the pattern, I'm just going to use that predefined name. And then also I'm going to issue here that I want full names to be returned, so the full path. Then I'm going to go ahead and print these raster files. I should see 4 here. And indeed, you can see actually 4. So those 4 were downloaded, and you can see here the pattern. So Swiss LT3D, and then 1, 2, 3, and 4. So essentially what I did, I just concatenated this main name with the ordinal number of every next file that is going to be downloaded. Okay, so this is fine. We have this done. And then the next step after this will be actually to load these raster files as a single virtual raster file. And this is what I would suggest you to do if you're having actually multiple raster files and you're downloading them. So using this Terra VRT and then passing here the raster files for the name of those files. All right, so once this is done, you can actually go and inspect. You will see here that actually we have dimensions of 4 by 4,000, so 4,000 by 4,000 pixels. The resolution is 0.5.5, so these are meters because we are using the metric coordinates reference system. And then here also you will see the extents in this coordinates reference system and the minimum and maximum values. Of course, 4,000 by 4,000 pixels might be quite a lot, given that we're going to be adding some more detail to our 3D map. So for that purpose, we can go ahead and actually aggregate this one. And aggregating is pretty easy because you can use a function from Terra. This function is called aggregate. And over here, you just need to pass the name of the raster file that you wanna aggregate, and then also followed here by this fact equals 2, which is then going to give you the disaggregated raster file. The second LIDAR data source is the one for Germany, and for that we can go to the OpenDEM.info, and over there we can search for this OpenDTM DE and then click on download. So over here, you can actually go ahead and select the area that you want. That is, of course, within these green lines, just like I'm going to do this here. And then you can go ahead and click on this download all files button, or you can just click on this link like I did over here. Once the file is downloaded, just simply head to your local folder. Over there, you can go ahead and unzip by clicking right click on this and then just selecting extract all if you're working from Windows. And if you're not, you can also unzip it directly in R. As soon as you unzip your folder, you will see here another folder created, so you can double click and open it just to see what is inside. And the second file from the left is actually the TIFF file. And you will see as I hover over it that the size of this file is 5.96 GB, so almost 6 GBs. And that is one of the, I think, the downsides of using that service to download the German LIDAR files. So they're pretty huge, and you don't really have the sense of how big of an area you selected because there is no, let's say, OpenStreetMap or Google Maps background map that will then kind of give you a sense of what you're actually doing. Because that file is really huge, what I would like to do next is select actually a smaller area for which I downloaded that file. And then within R, we're going to actually create our polygon based on these measurements here. And then what we're going to do next is simply crop that raster file. So I'm just going to zoom in now here and select approximately a way smaller area of that entire area that I have there. So I'm using here bboxfinder.com for that purpose. You can also check it out. And what I'm going to do then next, on the left-hand side, I selected create a rectangle, which I did. And then over here in the lower left corner, you will see this box. So you should go ahead, select these values here, and then copy them. We'll now go into R and create the polygon based on this bounding box values. All right, so we're going to start off by actually loading that huge LIDAR file using Terra Rust. And then here, as you can see, I actually first put the name of the folder, and then within that folder, the GeoTIFF file under the same name. That's because, as you remember, once we unzipped, we actually had the GeoTIFF within the folder with the same name. Okay, so once we do that, the next step would be to actually create here that polygon based on the values that we copied before. So I just kind of pasted these values here. And then the first one is going to be your X minimum values, so minimum longitude. The next one is going to be Y min, or a minimum latitude, then maximum longitude value, and finally the maximum latitude value. So having then these four values of your bounding box, we can go ahead and create a polygon out of it. So we're going to first call the stPolygon function from SF, then wrap around it this stSFC, and then we're going to here list and put together column-wise these two groups. So they need to be in a specific order. So we're going to first start with, as you can see, with the longitude values. So X min, and then followed by X max twice, and then X min, and again X min. And then finally another group, another list here are going to be the latitude values, where you start with the minimum latitude followed by twice maximum and once minimum latitude. And then finally here, very important, CRS. You need to define the CRS. So the one that we use is 4326. And then finally here, what you want to do is really make sure that this is an SF object. So that's why you are cursing this using ST as SF. And finally, we want to transform this whole polygon into the same coordinates reference system that is used by our DEM file here, DEM. All right. And once this is done, what you can do is simply go ahead and crop your large digital elevation model file with this bounding box like I did it over here. And finally, you can also plot this and see what you actually get here. So you should be able to see this very simple plot of the digital elevation model for that specific area of Germany. All right, the third LIDAR data source comes from the National Geographic Institute of Spain and covers the entire territory of Spain. So the first thing I'm actually going to do here is I'm going to use Google Translate within Chrome and then simply translate this from Spanish to English so that I can actually understand, and also you who are not speaking Spanish to understand what's going on. Then I'm going to go and click here on this search map just below this search bar. And then this is going to open a map, and I'm going to zoom in to some part of Spain. And then what I'm going to do next is I'm going to actually go to this left-hand side menu, and I'm going to select this first option, which is going to allow me then to select the area that I need. So I'm just going to click, click, and click, and click. And then the fourth one, I'm going to click twice to actually enclose this polygon. And as I click twice, this should actually show. This actually starts then searching for all the files in this area. Then, because the translation effect is now lost, I'm going to actually go ahead and again translate this to English. And then I'm going to go and search for this one, Digital Terrain Model MDT02. So that one, as you can see, it has two results, and I'm going to click on it. And this is then going to open this table here. Now, you might be actually wondering why it has two files, because we selected the very small area. That is because this service offers you files, one file with a local coordinates reference system. So that would be this first one. And then the second one is with the WGS 84, so the global reference system. It's only up to you whether you want a first one, which is metric based, or you want a second one, which is degree based. I'm actually going to go for the first one. And then to download actually this one using this ETR S89 or the other one, same thing, you actually need to go to the right-hand side of the screen. But before you actually download, maybe you want to see product details, like I actually am going to do here. So I'm going to go here to this eye icon, which is see product. I'm going to click on it, and then this is going to open information. I'm going to again translate, and over here you can see more information about it. So this is a 2-meter coverage. It covers the period from 2015 to present, so it has actually data from different periods, and you can see it's derived mostly from this LIDAR flights coverage, and it has information for the entire territory of Spain, and it comes in the form of cloud optimized geotips, which is also great for us. All right, you can also kind of check more information here if you're interested about this product. If not, you can simply just go back to the previous screen, and then if you want to download, you simply go to this right hand corner, and then you will see here this chart. So just beyond that, you will see the download icon. Just click on that, and that is automatically going to actually start a download of this file to a local drive. All right, going back then to your local folder where you downloaded, you will see here I have already a lot of other files, but this is the one that you need, the one that I selected. So the second one from the right hand side, this is the name that you should now go and copy, because we're after this going to go directly into R, use this name to directly load this raster file in R. Okay, so we're back in R. We're just going to go ahead here, create a raster file once more. We're going to go and list files, and then we just want to make sure that we kind of capture the right one. So our path is going to be the main directory. The pattern will be just the first few letters, so which are the names actually of that raster class, and then we're going to return the full names here. Then what we're going to do next is simply use TerraRast, and then pass this raster file to load then this raster file. Then we can go ahead and print this newly loaded file and see how actually this looks like. So you will see here that the dimensions are actually pretty large. So it's even larger than the Swiss one. So 4.8K by 7 almost 0.2K. You will see here resolution is 2 by 2 meters. And this is using this metric coordinates reference system. All right, so once you actually know this, what you can do next is aggregate. So kind of decrease the size of this one. So you can use aggregate from Terra. And then, for example, you can use the factor of 2. So you can actually decrease the resolution by 2 times. And then you can also go ahead and, for example, just visually inspect how this looks like using Terra plot and just passing this last object that we created. Fourth source of LIDAR-derived digital terrain model is the one for the United Kingdom, and is hosted here at the website of the Department for Environment, Food and Rural Affairs. So we're going to go to this then website, environment.data.gov.uk/survey, and then you will see here this OpenStreetMap dynamic map. You can start actually zooming in. And as you start zooming in, you will notice this grid, where each actually tile is at 1 meter's resolution. And also what is very useful here, you will notice it has also these shorthand names, which are going to be very handy as we select, for example, our area of interest. We're going to go ahead and select one of them, and we're going to make it actually small. So we're going to go and select this draw polygon on the side, and then we're going to start clicking here. And the last one, you need to click actually twice. And as you click twice, you will see here on this right-hand side that this get available tiles became green. So you can just click on that. And what is this going to do next is it is going to here prepare for you a download window where you can actually select here that you want to download this LIDAR composite DTM. For the latest year, in this case, is 2022, so that's very nice. And then you can choose whether you want 1 or 2 meter resolution. And once this is done, so if you have only one file here, you can either click on this name, or you can just click here on this download all, which is then going to actually start downloading the file directly to your local drive. Once the file is downloaded, you can go back to the folder where it was downloaded. And over here, you will see that it actually is a zip folder. And it's the one that I just now selected here. So what you're going to do next is copy the name of this folder, and then we're going to unzip it directly in R and load then the content directly in R. All right, so we're back in R, and first thing we're going to do is we're going to call unzip. We're going to paste the name of this zip file at extension zip. And then once we do that, we're going to go ahead and list what exactly we unzipped here. So we're going to put here the main working directory. We're going to take this, if you remember the tile name, and put it here as a pattern. And after that, we're just going to go ahead and see what we have. So what we actually got here, if you can see, we got several files, and one of them is the TIFF file. So we're just going to go and select that file name. And then we're just going to go and use Terra Rust for, of course, loading this single tile. And we also need to include this TIFF extension. And then we're going to check how actually this looks like. So this is a 5000 by 5000 pixels resolution or dimensions. Resolution is, of course, 1 meter. And as you can see here, we're using British National Grid. So a metric-based coordinates reference system, and you can also see here the minimum and maximum digital elevation model values. Of course, if this is too large a size of your file, you can go ahead and again aggregate, just as I'm going to do here. And again, I'm just going to aggregate here by the factor of 2 as well. And finally, you can go ahead and, as we did before, visually inspect this file by using TerraPlot. And if you did everything well, follow all the steps, you should be able to see a bit weirdly shaped raster file, but this exactly is the area that we selected, so everything is in good order. The fifth source of the LIDAR-derived digital terrain model is the Polish geoportal, so geoportal.gov.pl. And over here, we are just entering this portal. It takes a while it loads. And then you can, over here, just simply zoom into the area of Poland for which you want to download the data. What I really like about this one is that you also have a background map. It's not an OpenStreet background map. It's one of the Polish maps, but it's very useful to understand. And it's very crisp, and you can zoom in and get a lot of detail. Now, if you want to download this data, you need to head, just as I did here, you need to head here to the upper left corner. Luckily, everything is in English, so that's great. And then you need to click on this first one, which is called Download Data from WCS. So as you click on that, you will see that this new window opens up on the right-hand side. And this one is, however, in Polish. I didn't figure out if you can actually download, if you can translate it to English or not, but it's in Polish. And then you need to click here on this first one, where you need to select the service that you want to fetch. And on this one, luckily, there is indication in both Polish and English, and you should select the one which says GeoTIFF here. Once you do that, you need to click on this first, from the left side, button, this blue button, which is going to allow you to draw a polygon for which you want to fetch data. So you click on that, and then you simply click once and then drag for the area that you want. Now, if you select, like I did here, the area that is larger than 7 square meters, it's going to throw this error and it's going to ask you to draw a smaller area. So that's a bit of a downside of this LIDAR service, that you need to actually take, if you need a larger area, you would need to actually do, several times you need to go through this process. So then I actually click here on OK. And then I try to, I click again on this blue button and I try here to draw again, and then actually managed to do that with creating 6.52 square kilometers. So I was actually very close. And then once you select that, you just need to click on that next blue button here. So just next to this one, which has a pencil, there is this one with like a download icon over here. And as you click on that one, the download for this area of this GeoTIFF file will commence. Next, you need to head to the folder where this file was downloaded, and you will see here it's the third from the right hand side that I just selected, and it has a very generic name. It's just called Digital Terrain Model Format TIFF. And if you actually download more of them, they're just gonna have numbers appended here, at least in Windows. So it's quite easy then to simply load this one. You don't need to unzip or do anything else. You can just directly load this into R, which we're gonna do in next step. So we can just go ahead now and use Terra Rust and immediately load this TIFF file into R. And we can just kind of paste here that very generic name, add the TIFF extension. Once this is done, we can go ahead and just plot this file directly in R. This will yield a very interesting plot of this digital elevation model for that specific area of Poland. LIDAR-derived data terrain model number 6 is coming from Argentina, or to be more precise, Ministry of Defense of Argentina, which is hosted here at ign.gov.ar. So over here you will see, if you actually go to this webpage, you will see this interactive map. And then over here I tried selecting English, but it does not really react. What I actually quite understood from here is you can choose here the digital elevation model at 5 meters. The crispest one is 0.5, but this one does not have a wide coverage. Even this one at 5 meters does not have a wide coverage. So I simply then, zoomed in, and then you can only select, for example, a tile. So you cannot even, for example, search for a specific part of the tile. So you need to click then on that tile. And then in the next step, you need to click on this one and only link over here. And this is then going to download, of course. So it's going to download the file. But I also here selected, for example, this digital elevation model at 0.5 meters. And you will see only very specific and small areas, small chunks of land are available here for download. So I just went here for, this 5 meter one, just click here, click on the link, and this immediately then initiated the download. Once again, we go back to local drive where we downloaded. As you can see, I selected the zip folder that we just downloaded. It has this numeric name. So I'm just going to select here the name of this folder, and then we're going to go into R and unzip directly this in R. So over here in R, we're just going to go ahead and use unzip from base R. Then we're going to provide the name of that zip folder. And then once we unzip, we're going to use list files to enlist all the files that were actually unzipped in this process. And as a pattern, we're just going to use the name of that folder. Once this is done, we can go ahead and inspect this list files. And you will see actually here that we got two results here. One, of course, the second one, that is the zip folder. And the first one is, interestingly here, it's not actually a GeoTIFF file, it's an image file. Nevertheless, we're going to try and load it directly in R. So we're going to just copy this together with this extension, and then we're going to use TerraRust and see actually what it does for us. So after doing this, we will just going to go ahead and run this, and there was no error. So essentially, yeah, we managed to do that. We're just going to now go and print the content of this file and see what we're actually working with. And then you will here notice that it's approximately 5 meter resolution. The dimensions are, I would say, fine. So they are below 3000 pixels, both in terms of the width and the height. And you will also here see that this one is using the WGS 84 coordinate surfaces, so the globally used one. As well, you will see also the minimum and maximum elevation values, just like in other files. All right, once this is done, you can also go ahead and, again, visually inspect using simply TerraPlot, and then passing here this last file that you created. Finally, you should be able to see this plot that we created after running that chunk. The final 7th LIDAR-derived digital terrain model source comes from the United States Geographic Survey. And for this one, we'll first of all define the area that we need. That's why we are back in bboxfinder.com. And over here, what we're going to do, we're going to zoom in to the area of the Yosemite Park and take a very small chunk here. And once we actually define the rectangle that we're going to be using, then we're going to just fetch these bbox values that you can actually see here. And we should copy them because afterwards we're going to be going back to R and defining the polygon area for which we want to fetch this LIDAR data. So we're back in R, and the first thing I actually did here was to paste these coordinates for our bounding box. And then I just went ahead and start defining each of these 4 elements of this bounding box, starting with the minimum longitude and going to the minimum latitude, maximum longitude, and then finally ending with the maximum latitude. Once we have this, then I again use that previous method for creating the bounding box polygon. So using the SF package and 2 functions here, then put it into the list and column-wise binding, first of all, the longitude coordinates in a specific order, having actually here 5 of them, and then followed by the latitude coordinates, also 5 of them in a specific order, just like we did in our step when we were working on the German LIDAR data. Also here I defined that we were working with the WGS 84, so the 4326 datum. And then what is interesting here is there is a package in R which is called terrain R, and there is a function get tiles where you can actually directly programmatically get, based on your polygon, the data that you need. Now, I also used this in one of the previous tutorials to fetch this US LIDAR data and then create relative elevation models maps. And you can check that tutorial. It's pretty useful if you're looking for that use case. But over here, what I did was I again used terrain R. And then what I did was I first of all here define my bounding box. So this is the one that I want to use for fetching the data. Then for each of the files that will be downloaded, I actually put here that I want them to have this Yosemite prefix. Then I here used the largest size of them, so that would be 8,000. Resolution, I want 1 meter, so that's why I put here 1. And for the services, I also specified here that I want a digital elevation model. And also I included here verbose, so any kind of a message here that are going to be coming will be printing to us, so we will see them. So once actually this was downloaded, what I did next was simply use Terra Rust. And what I issued here is I issued actually element here, which is called elevation, as a part of this DEM. If, however, you are, let's say, now terminating your R session, what you can do is this file will be locally downloaded. So what you need to do is, instead of using this Terra Rust and then adding this DEM $ elevation, you simply need to provide Terra Rust, and then within the brackets as a string the name together with the TIFF extension, the name of the file that you downloaded. So it will be Yosemite and then something after that. You definitely need to check your local drive for that. And once this is done, you can once again just visually inspect this and see how it looks like by passing this final digital elevation model file that you created. And if you follow all the steps, then you should be able to see this very, very simple map of this Yosemite area, so Yosemite Village and some of the surrounding mountains. All right, so we now come to the second part of this tutorial, where I will show you how you can leverage a ray shader package in R together with OpenStreetMap data and create some very crisp 3D maps. Now, to do that, we're going to, first of all, I'm going to actually go ahead with this LIDAR-derived digital elevation model for that very small part of Switzerland. So that's why I'm actually heading back there to the end of that one. And then what I'm going to do next is, first of all, I'm going to convert the raster there. And what you will notice is each of them, whether it's for Switzerland, Germany, Poland, or any other part that I used in this tutorial, the last file has this DEM final. So essentially, you can just plug this one, any of these ones that you like, and just use from here. So that was the reason why I named them the same way. So over here, we're going to be using from ray shader this function, which is called raster to matrix, which is going to pass this DEM final to it. And then this is going to create the matrix, because ray shader works with matrices if you want to render the scene. And then I actually am going to use this MAR map and I'm going to use this topo colors, or e-topo colors. These colors, I used them also in the previous tutorial for creating some very crisp maps. So what I'm going to do here is I'm going to define, let's say, 16 colors, and then I'm going to create just a simple pie chart here so that you can actually see how this looks like, and then we can actually select a few colors from this palette and only use those for rendering our scene. And then from this then palette, I'm going to take values 1. So this is going to be like the highest peaks that have, let's say, snowy peaks. Then I'm going to go for 4 and 5. So these are going to be a bit lower mountains. And then I'm going to go for the values from 10 to 12, meaning 10 to 11 is going to be mostly hills, and then 12 is going to be really, really valleys on our maps. All right, so now that we know what we actually want, we're going to create this object pal. And then from the calls, we're just going to use those specific ones that we set. So values number 1, 4 to 5, and then 10 to 12. And then once we actually do this, we can again make a pie chart, but this time with this palette value so that you can actually see how this looks like. So this is going to be our palette, as we said before, starting with 1. So these are going to be these very, very high peaks, transitioning to mountains 2 and 3, then hills 4 and 5, and then together with this 6, this green, these are going to be valleys. Okay, as we define our palette, we can go ahead and render our first very basic topographic map. So we first of all put into pipe our matrix object. Then from ray shader, we're going to be calling height shade. So this is where we actually define the texture of our height shade. And then finally, we can use plot map from ray shader, which is then going to actually plot this very simple map in our editor. As you can see here, we just have our colors in place, but not that many details. So in the next step, we're actually going to play a bit with the shadows and make this a bit crisper map. So in this next step, what we'll be doing is adding shadow to emphasize slopes and depressions on our map. So we do have a valley, but we also have mountains with these lines. So we're going to be using add shadow from ray shader. And then within that, we're going to be using this ambiental shade. We're going to be passing this matte here, and we're going to be choosing for Z scale 6, so not very sharp. And then finally here, we're going to be selecting for the main layer, so the alpha layer, we'll be selecting this visibility of 0.2. So it's not going to be that visible. Our texture is still going to be dominating, but we're going to be having these very soft shadows, which are going to be emphasizing the slopes and depressions on our map. And when I said adding shadow to add a bit of a feeling of slopes and depressions, this is exactly what I meant. So finally, we have a bit of that 3D moment, but in the next step, we're going to be adding a bit more shadows to even make this crisper. Actually, in this part, we'll be adding shading, but with more details on the contrast, brightness, and the overall details of the image. So this is actually going to increase the complexity of our scene. To do that, we will be again using add shadow, and then within that we'll be using this texture shade. So we'll be adding actually the shading to the texture itself. Again, we need here to reference our mattes, but over here you will see I have 3 new arguments. So detail, the level detail goes from 0, so no detail whatsoever, to 1, a complete detail. So that makes rendering quite complex. I opted here for 0.9, so that means quite a lot of level of detail here. Now, other than that, there's also contrast and brightness, which you probably also know with working with images. And this too, you can actually play with. You can further increase or decrease one or the other and see actually what you get. But over here, I started just with these values so that you can get an impression how this would look like. But I definitely encourage you to try and see what do you get if you actually change these values a bit. And then finally, what we will do here is just add to this pipe here to the ray shader plot map, and then we're going to just replot this map again. Our map has evolved quite a lot by adding this shading, because now by having this additional level of detail together with the values for contrast and brightness for our texture, we're getting an even more realistic view, if somewhat darker. But again, I really encourage you to go ahead and play with those 3 attributes and see what really works for your own use case. And then one very last thing that I want to add here is simulating actually shadows, soft shadows, for areas with diffuse lighting. As you can see from our map, it got a bit darker, so I want to actually correct for this. So I'm again calling ray shader to rescue, and again the add shadow function, but this time I'm also using one more, which is the ambient shade function. So over here I'm just passing here this matte object, and then for this level of visibility, I'm simply putting 0.1. So they're going to be a very soft on our map, and still the texture is the one that is still going to be here in the focus. This is just going to add a very thin or very soft shadows to our scene, which you're going to see in the next step. All right, and this is our final topo map with adding those soft shadows for places with diffuse lights. In this tutorial, I want to go beyond the simple topographic map and start adding some of the features, such as, for example, human-made settlements or rivers, or for example, other elements. So what I'm going to actually do here, I'm going to go ahead and now load OpenStreetMap data for the specific extent that we're working on. And to do that, I first of all need to kind of convert our Terra Rust file, which is in that local coordinates reference system. I need to convert it back into the WGS 84 coordinates reference system, because the package OSM data for fetching OpenStreetMap data works with this one. So the EPSG 4326. So this is what I'm doing here. I'm creating this DEM new, so that's going to be a new object, so I'm not rewriting the other one. And then actually, the next step, I'm going to get the extent for our raster file. So I'm using simply ext function from Terra, and then I'm passing this DEM new, which has this WGS 84 coordinates reference system. And then in the third step, I will be creating then a bounding box from this extent. So basically, I'm just going to be taking the 4 coordinates of the bounding box from this DEM extent. And using this, then I can just literally go ahead and having this, I can use this to pass in the next step to the OSM data and fetch then the OpenStreetMap data for this extent. All right, having now this bounding box, we can go ahead and first of all fetch the OpenStreetMap roads. To do that, we will use OSM data package, which we used also in previous tutorials for that purpose. And then within this OPQ function, we'll be passing this DEM bounding box. After that, we'll be adding the specific feature name. So for roads, you need to use this highway string. And then finally, we want this to be returned in the SF format. So that's why I'm using this OSM data SF function from OSM data package. All right, then we can go ahead and actually inspect this data by printing this OSM data roads. And you will actually then see here that this returns actually a list of different elements. Now, intuitively, we know that roads need to be lines. So we are actually going to go here and search for OSM lines. So we see here there are 41 line strings, so that's fine. But it tells us here that the name of the geometry type we were searching for is OSM lines. So having that in mind, what we're going to do next is we're going to go back here, and then we're going to create a roads object, which is going to be kind of extracting this OSM lines. And then finally, we want to also make sure that this is in the proper coordinates reference system that matches the one of our raster file. And that's why we're here transforming it to that coordinates reference system. After fetching this data, we can go ahead and inspect it by printing this roads object. And you should be able to see this SF object in a typical OpenStreetMap fashion. There's actually a lot of columns here. Some of them might be useful, such as, for example, the highway column, which indicates, let's say, the type of the roads. And also here, it's going to show you the bounding box. And of course, that we are using here this local Swiss coordinates reference system for it. We're now going to go back to actually our ray shader code, and we're going to go back to the last part just above the plot map. And now we're going to be adding these lines to our scene. So from ray shader, we will call add overlay function. And then within this add overlay, we're going to call another function specifically for adding the lines. And this is called generate line overlay. Then we're going to add here that we want our roads. For the extent, we'll be using, of course, the extent of our raster file. Then here we can also set how thick this line is going to be. The default one is 1. We're going to be using 2. We're going to be using the white color for these lines. And then we also need to define here that we want to, for the height map, also use our matrix. And finally, we need to decide here actually how transparent, how visible these roads are going to be. Knowing that we might also have later on some labels over it, we're actually going to put here transparency level at 0.5 or actually 50%. And then we're going to just add here a pipe, and then we're going to rerun this entire code, re-render the map. And now we're going to see how these roads look like on our topo map. You can clearly see a very soft roads. This is because we did not opt for very high thickness, only 2. And also we opted for the transparency of 50%. So actually we gave way to the nature in this case. The beauty of the OSM data package is that we can continue adding more features, and this is exactly what we're going to do. So in this step, we're going to be adding another one, which is going to be a rivers and streamlines. So I'm just going to go here and copy this chunk where we were calling roads and just replace with rivers. And importantly here, the way that rivers are classified in the OpenStreetMap terminology is called waterway. So essentially in this add OSM feature part, you need to replace highway with waterway, and that's basically it. After that, we can also copy this other chunk. And because rivers are also lines, we're just going to change here the name. So we're going to keep the OSM lines, and then we're going to just rerun this code again and fetch those roads. So once we fetched the OSM river data, we go back to our radiator code, and then we now start adding the rivers also. Now rivers are also lines, so we essentially are going to use the same chunk of the code that we have for the roads. So generate line overlay, and that's why I'm actually just pasting here this whole thing and replacing roads with rivers, and also here readjusting the line width. So I'm actually gonna make rivers a bit thicker, so I'm using line width 5. And also for the color, I'm going to be using this very nice deep sky blue color, everything else remaining the same, and just having a pipe here finally to the plots map to re-render our map. You will see now rivers clearly standing out. So this is this blue color standing out, and as you can see, of course, it's thicker than the roads. We can continue playing with the OpenStreetMap data and of course add human footprint to it. So we'll be calling OpenStreetMap API again to get buildings. Again, I'm just copying and pasting here and replacing things. But one thing to keep in mind again, for the buildings, the key name is building in the OpenStreetMap terminology. So we're replacing this first chunk with it. And then the second one, apart from the names, which is buildings here, we also need to replace this OSM lines, because buildings intuitively are not just lines, they're actually polygons. So we need to use here OSM polygons instead, and then keeping everything else the same. Once again, we're going back to our radiator code here, and we're going to add yet another line. This time we'll be adding buildings to our plot. So over here we're calling radiator add overlay, but instead of generate line overlay, because we are working with polygons, remember, we need to have generate polygon overlay, which is a bit different from the generate line overlay, and we'll see how. First of all, we're going to be adding buildings here. Second, also the same extent, which is our raster file. Then we're going to have also the line width. I'm going just for 2 here. And then we're going to have here line color. Now I'm going here for the dark red color. Line color means the color of the lines of our polygon, but there is an additional argument for filling the polygon, which is called palette. So I opted here for the same color of the lines of the polygon and of the interior of the polygon. And finally here you need to define also the height map, which is your matrix, and then simply rerun the entire code. In the newly generated map, you will also now see a couple of these red dots indicating human footprint, or in other words, the buildings from the OpenStreetMap data. To improve the context of our map, we will also now adding the names of the places, so towns, villages, hamlets. And again, we will call to rescue the OpenStreetMap data, in this case OSM places. Again, we're going to be copying here and pasting this chunk and checking also what these places mean, because we want to also fetch the names. So in this second step, what we're going to be doing here is we're going to be fetching the places. Places are points. So that's something also we need to change here. Instead of OSM polygons, we're going to put in here OSM points. All right, and then what we can do is we can then go and inspect actually these places. And as you inspect this file, you will notice here there are fewer fields, but the one that is important for us is this name field. We'll be using this name column to render the names of these places for our extent in the actual ray shader map. And now that we have the names, we can go ahead and also re-render our map. Once again, we're going to be using add overlay function from ray shader, but this time we also need to use another yet function within this one, which is a generate label overlay. So within this one, we'll be adding places as our main data. For the extent, it's going to be our raster file. But then we need to add a very different argument, which is called text size. This one determines the size of the text. So that is one of them. The other one is the point size, which is going to be the size of the point if you want it displayed. This point actually is the coordinate place of this specific town, village, or hamlet. And then this argument color here is going to determine the color of both the text and the point size, or point. If you want a separate color for the point, you need to use point color in this case. But I'm going to go just for the white color for both the size of the label, or actually the color of the label, and the color of the point. And finally here, apart from the height map, you also need to define this very specific attribute to this generate label overlay function, which is called data label column. Over here, you need to put the name of the column in your data, which has information about the place name. All right, and this is our final map, at least the 2D version of it, which now has not only the topography, roads, rivers, and buildings, but also the names of the major places in this area. Because we want to turn this map into a 3D map, we're actually going to go to our code here and then replace this ray shader plot map with a ray shader plot 3D. So this will then generate a 3D scene. And within this plot 3D, we need to specify the name of our matrix. The Z scale essentially should correspond to your resolution. So in our case, you remember that we aggregated a resolution of 0.5 to 1. So we are choosing the Z scale of 1. If your resolution is, for example, at 2 meters, then I suggest that you use 2. If you're using something higher than that, then your map is going to get flatter. Or if you're using, let's say, lower than 2, then it's going to become more rugged. Then we're going to go here for the shadows. Solid false means that I don't want to have anything around the map itself. So I want the map to be like as a map. I want very soft shadows, so that's why the shadow darkness is 1. 0 would be very, very sharp, very strong shadows. The window size will be 600 by 600 pixels. This is, of course, dictated by the fact that I have a rectangle of 2K by 2K. And then finally here, I also chose for the angle degree 85. So it's going to be almost flat. And then theta itself is also going to be here 0. So I don't want anything tilted around the axis. And then finally, also, I'm going to choose here the zoom of 0.5. So zoom of 0 is completely zoomed in and zoom of 1 is completely zoomed out. So somewhere in between, and then we'll see how this works for us. And once you render the scene, you should be able to see a map like this. However, you will notice that some of those place names have been cut off. So we're actually now gonna a bit expand this render scene. So we're gonna readjust it without, again, re-rendering the entire code. And to do that, you can use another function, very useful from ray shader, which is called our render camera. And within this one, you can readjust, for example, your zoom level, just what we want, but you can also adjust your degree angle, and you also can adjust this theta value, or whether it's tilted around the angle as well. So we're going to just a bit increase the zoom to 0.51 instead of 0.50. If you don't want to venture into rendering 3D map, and I know it can be painful for most of the computers these days, you can also go ahead and simply render your snapshot, which is going to take something like, within a minute time. So you can go ahead and use this render snapshot, and then you can provide the file name so that you can save it locally as an image. And also, Optionally, you can choose this software render equals true, which is just going to make the image a bit crisper, but it's also going to take more time. If this is, however, a problem for your system, you can then choose software render equals false and just omit it. And this is how the snapshot will look like, essentially very similar to the render scene itself. But this is not all. And at least for me, the main fun is rendering this image as a 3D map. So what we're going to be doing next is, first of all, making sure that we download this lights, specific custom light that we can use for our scene. Of course, I'm using this from the Polyhaven website. Don't worry, I will include a link to this specific one in, of course, the GitHub repo, but also in the description box below. And then we're going to just download this HDRI file locally to our drive using, of course, the download file from base R, and specifying here the name of the destination file, which is going to be simply the base name of our URL, which is again this HDRI file, and then again using this binary mode for downloading this file. So once we have our custom light downloaded, we can start writing a code that will help us render this 3D map, and that includes using render high quality, which we use so many times before. So first of all, you need to define the name of your file together with the image extension. In our case, that's going to be the PNG file. Then I would like to see the preview as the scene or as the map gets rendered together with the progress. Light equals false here for a very simple reason, because we want to use environment light, and that's why I'm here defining what is our environment light, as well as intensity. Intensity of 2 works well for this, but be careful, because you might need to increase or decrease the intensity depending on the type of the light file that you downloaded. Also here, I'm going to rotate the light by 90 degrees. I'm also going to here utilize the parallel CPU running. And I'm going to also define here the width and the height in terms of the pixels. So I'm just going to use the same width and the height that my raster file has, so 2000 by 2000 pixels. But you can also play around with lower or higher resolution depending on your needs. And finally here, I'm going to turn off the interactive mode, which allows you to actually move the scene as it gets rendered, because I don't want my current R session to crash. All right, and this is the final map, the rendered 3D map, where you can clearly see the mountains, the high peaks, also these very soft shadows, but also very important OSM features such as roads and rivers, then buildings in red, and also combine that with the place names, which give away more context also about the specific extent. And this is how you do it. In today's tutorial, you learned how to access 7 free LIDAR-derived digital terrain model datasets, and then how to turn them into super crisp 3D maps in R combined with OpenStreetMap data and with the help of the amazing Ray Shader library. I'm really looking forward to your own use cases and how you take this tutorial to a journey across the world. If you, however, would like to replicate today's analysis, I prepared the link to the GitHub repo in the description box below. So do check it out. Feel free to reuse it, modify it, and change it as you see fit. Also, if you're new to this channel, I suggest warmly checking out some of the previous tutorials, which might help you get familiar with 3D mapping and using Ray Shader in R. If you have any questions or comments, feel free to leave them here in the comment section to this video. See you next time.